Morning, everyone.
Good morning.
Good morning, sir.
Okay. I think there are 61 participants. Okay. Hari Prithvi Hemo, please change the display name to your roll number, man. Hari Prithvi and Hemo. So what were we discussing in the last class? Here.
Maximum power transfer theorems.
Yeah, we were talking about theorems and some problems related to all the theorems, right? In the previous class, we solved problems for theorems such as Thevenin's, Norton's, superposition, reciprocity, and maximum power transfer theorem, right? So I think that that is enough for theorems, and I have sent you the material regarding network theorems, right? Did you go through that material? Have you seen that material?
Yes, sir. Soon.
Is that okay? Is that sufficient for theorems part?
Yes, sir.
Yeah. So just go through that elements, right? What are the problems you have, tutorials you have? Fine. So just I think they are very you can solve them easily, and if at all you have any doubts, you just we'll discuss them in one of the hour in this week. So let me know how far you can solve the problems which are in examples or tutorial problems. Fine. So I think we have some lab session tomorrow. So if you have any doubts, you can come up tomorrow because we have 3 hours of slot, right? We'll be discussing about something for theory topic for syllabus, and we also discuss about worksheets for BW lab as well. Somehow we have to carry forward the lab as well, right? So we'll split that 3 hours of class into two half. One first half I will take the theory for BW, and next half we will be talking about the lab, and I'll tell you how to write the worksheets, right? And you can upload the worksheets as if you have done the lab, right? I will explain how to do, what to do, and if possible I will show the simulation, right? You can take the values from the simulation itself. Okay. So on the day when we were talking about introduction to AC fundamentals, right? The strength was very less, and I promised that I will be taking that again. So I think I will I utilize this extra class which I got today. Fine. Raju sir was on leave, so I just got an extra class. So I will try to compensate or use this for introducing you the AC circuits once again. and it will be a revision for those who are attending on those who have attended all the class on that day. Is that okay?
Yes, sir.
Fine. So let us go for talking about AC fundamentals. Let me share my screen first. Second. Share the screen. AC fundamentals. Okay. Is my screen visible?
Yes, sir.
Yeah. So give me a second. 1 second. Rajendra, sir. Yeah. So is the screen visible? Okay. In this topic, we'll be discussing about we'll discuss about introduction to or fundamentals to AC circuits, and what's the need for an AC circuit. How do you generate a single phase voltage, and what's the relation between time and angle there? And we have certain values in AC. What are they? We have some maximum value, average value, and RMS values, form factor, peak factor, phasor representation of sinusoidal waveforms, voltage current relationship in pure resistor, inductor, and capacitor at steady state, analysis of single phase AC circuit resistance, reactance, impedance, conductance, susceptance, and admittance. This is the syllabus which we have, or I have just small changes. I have included some more topics than your which are not in your syllabus, but which are effective for learning, right? Or which are effective for understanding. So let us go for AC circuits first. And why the AC generator, or what's the need for AC circuits? So what is actually AC means, or AC voltage means? It's alternating current voltage, right? So what are the different types of sources we have for AC generation is, see, somehow by default we will be using this type of waveform, right? So, what do you call this waveform as? Since this waveform follows a sinusoidal property, so you call it as a sinusoidal waveform, right? And this is a square wave and this is a rectangular wave. All are examples for alternating currents. The waveform could be any of these or all these three are called as alternating current waveforms, AC waveforms, right? So what are the sources that generate AC? We know that alternators, that is AC generators. We have windmills that can be converted in which will be using a double DFIG, double fed induction generator, and solar where you get DC supply that can be inverted using an inverter. And many sources we have diesel engine which is connected to an AC generator, whatnot. Whatever the outputs of all these will be in terms of AC. That is, I will tell the importance why you also use only sinusoidal, but usually most of the cases we will be, or 99.9% will be using this type of waveforms for as AC waveforms, sinusoidal as AC waveforms. And in general, there are two types of current which we usually know that there are two types of current. One is DC, direct current, and another one is alternating current. So what is the difference between these two? Direct current flows in only one direction, whereas alternating current will fluctuate from which will flow to and fro in a circuit, right? So what is how do you know that these are alternating? How do you represent them? That is how we represent the circuit, right? How we are representing the circuit now here? We are representing that with alternating waveform. That during this you call it as positive cycle, this you call as negative cycle, right? Suppose if this is considered as positive cycle, we can assume that the current is flowing from source towards the load, right? In one direction. This is load. So the current may flow in this direction during positive half cycle, and it will be reverse. It should be reversed when it is flowing in the reverse direction, because we are representing them into opposite directions, right? Positive and negative cycles. So this is how you represent the AC waveform. So there will be a to and fro motion of the electrons when it is AC circuit. A DC current will flow directly from source to load and back to source. It will go its path, whereas alternating will be fluctuating to and fro between load and source. This is how we can represent them. Positive half cycle, the charge direction is indicated from left to right, whereas in the next half it will be. So if the time period for this alternating waveform, if this is a square wave, this alternating waveform is for a time period of t, for t by 2 period you consider it as a positive cycle, and during positive half cycle the current electrons flow from left to right, right, as shown in this figure. And if in the other half we call this as negative cycle, and the electrons will flow from right to left, reverse to this. As simple as that, right? So this is how we represent a sinusoidal waveform. And let me talk first about sinusoidal alternating voltages and currents. So in general, all the commercial or alternators will produce a sinusoidal waveform. Don't ask me whether it's a pure sinusoid, but mostly it should be a sinusoidal waveform. And in a practical condition, we definitely won't get a pure sinusoid, but we'll get some harmonics in between. That is not up to us. You just learn that you will be assume that you will be having a pure sinusoidal waveform that is generated from a commercial generator or any alternator, right? How do you produce it? How this voltage is produced? I will just explain how the voltage is produced or in general. And I think we already discussed what is the source for alternating or this voltage to be generated. What is the source we consider? We consider that a alternator, or say, what do you call this as? AC generator, right? Which is coupled to a prime mover. Let me call this as a alternator or AC generator. This generator is a usual word which you already use. So I can consider this as AC generator. It is coupled to a prime mover. What do you mean by prime mover in general? What do you mean by prime mover? Someone there? What do you mean by prime mover? So what's the function of a, okay, let me give a brief introduction to machines, right? So what do you mean by machine? We were talking about machines, right? In lab as well. BW lab, you have some machines experiment as well. And from unit 3, you deal with machines, right? Okay, what do you mean by machine? I think you heard about something called as these two terms. What is it? Motor and generator. First one is motor, second one is generator, and third one is machine. So what do you mean by motor? What do you mean by okay, takes in electricity to do some useful work. Okay, so what is the difference between motor, generator, and machine? What is a machine? What is a motor? What is a generator? I think you will be hearing this here and there, right? So what is the difference between a motor and generator? Okay, motor and generator are machines. Fine. Yeah. Generator gives out electrical energy. Fine. Good. See, a machine could be either a motor or a generator. That's it. So machines or can be classified into two types. One is motor and another one is generator. So what is the function of a motor? What is the input for a motor and what's the output we expect? What's the difference between input and output of a motor and a generator? For motor, we give electrical input and what we expect the output as mechanical. What happens to generator when it comes for a generator? We give mechanical input for the generator and we expect electrical output. That's it, right? Is there anything else than this? Yeah.
Or can we call them as active and passive elements?
Yeah, in terms of if you consider them as circuit elements, right? We are not considering them as circuit element, but if you consider a motor as a, see, we represent every electrical component in terms of equivalent circuits, right? So whenever I consider electrical motor, I can represent it with the electrical equivalent circuit. Then we use all the resistor and inductor components for representing the motor, because in general, what's the physical representation of motor could be? Motor could be can be represented something like this, right? As front view of or side view of the machine. That's it. You consider this as either motor or a generator. Doesn't matter, right? As it is, we can't consider them as active and passive elements. But when we represent them with the equivalent circuit, which consists of some resistor, inductor, right? Some components, then since the R and L components are involved in this, we can consider them as passive circuits or passive elements. Understood? As a motor or directly as a motor, you can't consider them as passive elements because we are talking about elements. Element motor doesn't come as an element, right? Either it comes as a utility or it comes as a source when it comes for a generator. Am I clear?
Yes, sir.
Yeah. So so now such we will talk about motors later on, but when it comes for the generators, what is the input we have to provide is mechanical input, and what's the expected output is electrical. Since it's a AC generator we are talking about, the output will be assumed to be sinusoidal in nature or alternating in nature. Okay. So now what is the input we give here? How do you provide the input for the generator then? By using a prime mover. That's what I said, right? What are the equipment? What are the equipment we are using here to rotate the or to feed mechanical input for the generator? We call it as a prime mover. What are the examples of prime mover? I've heard about windmill. Yeah, windmill or what's the other one? Turbines. steam turbine, water turbine, whatnot, everything. Yeah, windmills, good. Any other examples for the prime mover? You can even use a motor as a prime mover for the generator, no issues, isn't it? Wherever there is no scope of using a diesel engine or called as diesel engine. If there is no scope for using a diesel engine or a wind turbine or a steam turbine, I can use a simple any motor, AC or DC motor as a input prime mover, right? So what is the fundamental function of these elements which I use here as a prime mover? What is the fundamental property of these should be, or function of these should be? To provide mechanical input for the machine or for generator, right? Since it is acting as a generator, it has to provide the mechanical input, right? And it will convert, the generator will convert that mechanical input to something as electrical output. If it is a single phase generator, it will get two terminals, phase and neutral, or if it is a three phase generator, it will give R, Y, B. That's it. So out of these, we are interested in a single phase waveform. So I will explain how you generate the sinusoidal, but what's the need for using the sinusoidal? Why only sinusoidal? And see, the sinusoidal waveform can be expressed in general with this expression. What is that? Since we use the small letters V and small I for representing instantaneous values, right? So in AC circuit, since it's already varying with respect to time, the magnitude doesn't remain constant for any voltage. So what we do is we represent every time we present with a instantaneous value, that is small v, right, which can be represented as a product of v maximum into sine and omega t. What is omega t? Is the angular velocity of the coil. I will explain what this could be, right? So now, since this property of the waveform is sinusoidal in nature, we know that you have studied about the sine characteristics, right? And you know that what happens with the variation in sine angle, 30, 45 degrees, 60 and 90, right? What are the values you have here? Sine 0? 0. Sine, yeah, sine 30?
1/2.
Yeah, sine 1 by 45?
1/√2.
Okay, sine 60?
√3/2.
And 90?
1.
Yeah. If we go on writing this for next, right? What is the next one? 90 plus 30, 120 and 145, 45, I thought 135, and another one is, if I go on writing this for another sequence, right, or opposite to this 90, what is the difference between two is 630, right? So 120, 135, what is the other one? 150 and 180. What are the values I get here? I can rewrite them in the descending order, right? Suppose if I could write them here 0, 30, 45, okay, 60, 90, 120. What's the value here? 135. Sorry, 135, 150, and 180. So what's the values I have here? 0, 1/2, 1/√2, √3/2, 1. This will be √3/2, 1/√2. This will be 1/2, and this will be 0. So if I plot them on a graph with respect to degrees here, right? What's the value I'm going to get? Is same as this, right? This value maximum. What's the maximum value I go? Okay, what you are going to get here is 1, right? Where you are going to get that is at 90 degrees. This is how Y called as a sinusoidal waveform, right? Is that clear? So we can find the magnitude of this instantaneous value of voltage by using this sinusoidal property, right? And where it is also associated with some term called as maximum, that is the peak value of the voltage which you get here, you call it as maximum voltage, and omega t is the angular velocity, right? We will go into angular velocity later on. Fine, you just remember that you will be having omega t, which is nothing but the angular velocity of the coil. So similarly, when you have a sinusoidal voltage produced, when I feed it to a resistor or some element or a passive element, right, definitely it will produce some current, and whose since the voltage is sinusoidal in nature, the current will also follow the same. And it depends on the various elements through which it is made to flow. But fundamentally, the response, if V is considered as excitation, I is considered as response. So since the excitation is in sinusoidal nature, definitely the response should follow the excitation. So similarly, we can give a representation for voltage here. The same representation can be given for current. Maybe the magnitudes may vary. Let be this be 200 volts or this could be 20 amps. Doesn't matter, but they will follow the same sinusoidal waveform. The nature of the output relation between input and output remains the same, right? And what's the need for why only sinusoidal waveform? Why you are very particular about the sinusoidal waveform? We can produce sinusoidal alternating waveforms in different shapes. What are the different shapes we considered? Square wave, triangular wave, rectangular waves, etc. What not? We can produce in any form, right? If the But what happens with the sinusoidal? What's the advantage we are going to get in the sinusoidal waveform is that the sine waveform produces least disturbance in the electrical circuit and is the smoothest and efficient waveform. It is the smoothest and the efficient waveform. So that's the reason why we stick ourselves or we confine ourselves for producing a or using a sinusoidal waveform as a fundamental AC quantity or fundamental AC parameter. That's the reason why we are comparing only AC with DC, but that is to sine. In AC, we are taking only sinusoid because that's the efficient of all these. So we are going to use only such sine wave. And we know that when we consider the AC loads, right? What are the examples of AC loads we have? Tell me some load examples for AC loads or load. What are the examples you have in a load? So what's the supply we are going to get in our home? What's the type of supply we are getting in the home, AC or DC? Yeah, you're going to get AC in your home, right? What's the value you are going to get at home? We generally call it as single phase AC 230 volts, right? Right.
240.
Yeah, single phase AC 230 volts, right? So what does it indicate when you say it as a single phase AC here? And whatever the loads you have at your home, see, except lighting load, most of them are inductive in nature, right? Say, you consider, for example, if you have a fan, right? It's a type of example for inductive load. You have a refrigerator where you have a compressor. Compressor is nothing but a motor, a single phase motor. So it just works on the principle of induction. So you call it as a single phase induction motor, right? So most of these loads are what type of loads they are using at home is inductive nature. So whatever the supply we are generating, that should give what say best output when used with the loads. So if I have inductive loads and if I am going for a square wave of generation or square wave of input, what will happen? It will not be smooth. So the average value of inductor, you know that inductor doesn't allow sudden changes in current. But what happens when I feed it a smooth sine wave? What happens if I feed it? What will be better? What do you think? Which one is better? Feeding a inductive load, whether it is a square wave or a sinusoidal?
Sir, sine wave, because there are the means the decrease is very gradual, very smooth.
Yeah, even if I give the same
Sharp
square,
turns are not there.
yeah, even if I give the same square, since you have a sharp edges here, the output waveform of current will not be same, and it is see. If I give a sinusoidal waveform, sooner or later the output current will also follow the same thing, same wave. But if I feed this a rectangular waveform or a square waveform for a inductive load, definitely it will not follow the same. It will either it may result in some waveform like this. Might not be pure sinusoidal, but instead of getting a square, right, we are expecting to have a square waveform like this as current, right? But what will happen? It will not follow the same. So when the relation between input and output are not followed, definitely this is not going to be the best output we are going to get. So most of the loads we have is inductive and reactive in nature. So that's the reason we follow the sinusoidal, right? Which gives some best output. So how do we? This is how we represent the instantaneous values in AC. What are they? A instantaneous value will be represented as some product of maximum value into sine of time angle. Sine of time angle. What is the time angle? It's omega t, right? And these are the points to be noted that it may be noted that alternating voltage and current means always means sinusoidal alternating voltage and current unless stated otherwise. So if you are in your problem, if you are mentioned with the signs alternating voltage and current, by default we consider them to be sinusoidal until unless they are mentioned. Am I clear? So if you are mentioned with, say, if you have a consider alternating voltage of with a peak magnitude of 230 volts and a angular velocity omega t is equal to a 314 314, then you have to assume it to be a sinusoidal waveform. No need to mention it all the time that it's a sinusoidal alternating voltage. But if it is a rectangular or a triangular waveform, they will clearly mention that it is either a triangular wave or which type of alternating voltage it is, right? Until unless mentioned, we consider them to be sinusoidal alternating voltage and current, right?
Sir, but isn't AC supply simple harmonic, sir? So we follow the sine graph because simple harmonic motion also has same graph.
Yeah, same. See, 90% of the things in your environment are sinusoidal in nature.
Yes, sir. Yes, yes.
Yeah, I thought of saying that, but it will become more philosophical, right?
No, sir.
Because you already heard this when you study your inter, right? All the things which physics teacher taught you, right? He
Yes.
might have given example of a simple pendulum. He might have
Yes, sir.
given
Yes, sir.
the waveforms in a river,
More emphasis at
tides.
waveforms, sir. Yes.
Yeah. So most of them will be sinusoidal in nature, but technically speaking, okay, that's fine. You've already learned them. So happy for that. No issues. Fine. Done. So this is how we calculate the sinusoidal alternating currents. What happens? We can segregate them into 4 segments. The and we can do the calculations. This is not that required. See, so this is a waveform for a 2.5 cycle waveform. So we need some definitions. What do you mean by instantaneous value? What do you mean by peak value? What do you mean by peak to peak value? And what is frequency? Let me define them. What do you mean by instantaneous value? What do you mean by instantaneous value of a alternating current or alternating voltage? What's the definition for instantaneous? What is the meaning for instantaneous value? What could be the meaning for instantaneous value of current or voltage?
Sir, dV by dt, I think.
No.
Differential of
In general. Yeah, value
at a
of
particular
the
time.
magnitude of the parameter, whether it might be a voltage or current at any particular time instant. Say I have some time, it may be this might be at some time t. What is the magnitude I am going to get here if this is a voltage cycle? So what is the magnitude I am going to get here is the instantaneous value, isn't it? So what do you mean instantaneous value is the magnitude. Yeah. So the value of the either voltage or current or value of the alternating voltage or current at any particular time instant or in any particular instant of time, you call it as instantaneous value, right? So, and what do you mean by maximum value? What does it mean by maximum? We know that alternating waveform is going to change from vary between some particular limits, right? from, you can show it as minimum to maximum, right? Or I can specifically say that between 0 and 2 maximums. What are the maximums you call it as? What maximums you call it as? Positive maximum, negative maximum, right? This is positive and this is negative. So what do you mean by maximum is the highest peak or highest value acquired by this waveform is known as maximum value. The highest value acquired by the alternating quantity is known as, what do you call it as? Maximum value. Am I clear? So the I'm just talking about the magnitude. I'm not, we are not we don't have any problem with the polarity, right? Even if I can have a magnitude of 10 maximum peak here, it will be minus 10 maximum here. So we are not interested in the polarity, we are interested in the magnitude itself. So for any AC waveform, definitely will be having a positive peak and a negative peak. But what actually maximum value mean is the magnitude of the peak value or highest value. The highest value acquired by any alternating quantity is considered as a maximum value, right? So what do you mean by peak to peak then? What do you mean by peak to peak value? As I said, we will be having two peaks, that is positive peak and negative peak, and any value, the value between the magnitude between these two peaks is considered as peak to peak voltage. So when you go for electronics labs, we will be much interested in finding peak to peak values in the electronic circuits lab, right? So what do you mean by frequency then? What do you mean by frequency?
Number of cycles per second.
Yeah, number of cycles per second.
Second.
The periodicity with which the waveform repeats, right? You call it as frequency, right? And is given with the equation here, which is inversely proportional to the time period. Because if I have more time, I will be having less frequency for each cycle, right? See here, this T3 or T1 is considered as a complete cycle, right? It may be varying from, see, what is the difference between T3 and T1? How they are, is there any difference between these measurements?
No.
What is the difference here is, in T3 we are considering from 0 to 0 instant, whereas T1 we are considering from some point of time after 0 to some same point of time after the cycle. So fundamentally, what do you mean by a cycle of voltage, or what do you mean by cycle, which consists of a positive and a negative wave, right? So we consider them as, let me say I consider this as a half cycle. So what do you mean by half cycle is either might be a say either a positive wave or a negative wave. From 0 to 0 we call it as a half cycle. From 0 to 0, where it might start from the, I'm talking about the magnitude here. These are the three instants of 0 magnitude of the let me consider this as a voltage waveform of the voltage. So any value between 0 and 0, or the time period is not same. This is 0th time period, this is 180th, and this is say pi, and this is 2 pi, right? We know this. This is pi. So half cycle is between 0 and 0, and what do you mean by full cycle? A positive half cycle and a negative cycle, negative half cycle will comprise a complete cycle. And the time taken, okay, the reciprocal of time taken for these you call it as hertz, frequency, which is represented by hertz, right? The repetitions which you, the time taken for the repetition of alternating quantity is called as time period. What is this T1, T2, T3 does mean? We can calculate it from either from 0 to 0 instant, or from peak to peak as shown by T2, or from a particular instant to another particular instant in the repeating waveform. You call it as a time period, right? And time taken for starting a repetition, you call it as a time period, right? And reciprocal of such time period, you call it as a frequency. See, you find the variations here, right? T1, T2, T3. What is the difference it makes? All are one cycle, but the measure, the time, or the Instant to instant, measurement of the cycle is different in each cycle or in each case. Am I clear? So this is what it means. See, if I have a waveform which takes 1 second of time, right? What is the frequency I have here? What does it mean? What is the frequency given as 1 by time period? What is the value? 1 by 1. You got it as 1 hertz. That is, I will be having 1 cycle per each second. 1 cycle in the sense 1 positive half cycle, 1 negative half cycle over a second. And if say, if I have something like this, how many cycles I have in this second example? In a time period of 1 second, how many cycles I have?
2.5.
Yeah, 2.5, right? So how many, what is the time period I'm going to get here now? Divide this time period of 1 second into 5 limits, right? This is 0th limit, 1, 2, 3, 4, and 5. What's the time period between each instant? If this total time period is 1 second, what's the time period between each instant now? It's 0.2 seconds, right? Yeah. So for a complete cycle, what's the time period I'm going to get? T is equal to 0.4 seconds. So what's the frequency I'm going to get here? Frequency is equal to 1 by time period. What's the value I'm going to get here? 2.5 hertz. Isn't it? Yes or no? Am I clear with this?
Yes, sir.
Yeah, frequency is the number of cycles per second. So I have 2.5 cycles per second here. So I call it as 200 of hertz. That's it. Clear? Yeah. So we have some examples. We can determine this. I will share the screen PPT with you. You just go through them, right? Fine. And before going to addition of the sinusoidal, let me explain how the voltage is generated, right? So we will talk about generation of the sinusoidal waveforms. Let me take here. So who defined the principle of AC generator? What is the principle of generation? Have you heard about something called as Faraday's laws of electromagnetic induction? Heard about it? Faraday's laws of electromagnetic induction. So what does the statement mean? What does it mean? What is the statement supposed to say? Faraday's laws of electromagnetic induction. How many laws you have? Sia, do you have the attendance? Are you able to see the attendance, students who are present today?
Sir, I'll take it now.
Yeah, I think you can directly follow the attendance list. It is, I think you can, there are 60, other than me, there are 61. So you can easily identify who are the absentees, right?
Yes, sir.
Yeah, you just post them. Okay, you just send them, message me, okay?
Okay, sir. I'll do.
Fine. Okay, done. And okay, what are the Faraday's laws we have? Two laws. EMF is differential of flux over time. Okay. Okay, fine. Yeah. What is the statement you said? EMF is differential of flux over time, dphi by dt. Good. Okay, fine. So Faraday's laws of electromagnetic induction. We have two laws of Faraday's laws. Faraday's laws are of two types. What are they? Law 1 and law 2. What does they give? What does they give? What is the definition they give? E is equal to d phi by dt. That's what it is. If the EMF induced what? They give relation between EMF and flux. Okay. Fine. Okay. Somehow, whenever conductor cuts a magnetic flux, an EMF will be induced in the such conductor. Or you can also state in other way that whenever flux cuts a conductor, an EMF will be induced, and such induced EMF is proportional to d pi by dt. Right? These are the two statements or two laws given by Faraday regarding the EMF induced in any conductors. Here, so based on that property, we apply this property for EMF generators, right? Where the value of we can take a generator and we can apply the same principle whenever a conductor cuts off flux, and we also have some right hand rule and left hand rule, Fleming's right hand rule and left hand rule, where we can define the direction of the EMF induced in the generator when other parameters are mentioned, that is the direction of rotation and the direction of flux, right? We can identify the direction of the EMF induced. So we will continue the same in the fourth hour from 12:40 to 1:30. Fine. Now let me, I will stop class here. We will continue the same in the fourth hour. Is that okay? One second. Okay. Thank you. See you again in the afternoon.